Now, in terms of actually interpreting experiments, let me just add one more point that I've kind of glossed over so far, and that is that, well, I said that when you talk about electrons in a solid, one of the very important simplifying concepts that people understood in the early days of solid-state physics is that electrons in a solid behave almost as if they are in vacuum, but with a certain energy-momentum relationship. That it may not be p square over 2m as in vacuum, it could be something else, or it could be a different mass. But given a certain energy-momentum relationship, you could understand the behavior of electrons in a solid. Now, to that, there is one more concept that we need to add, and that is that in solids, often there are multiple valleys involved. So, actually, even ordinarily, electrons, there are these two spins that you have to account for. So, right now, I never brought that up. We said that, well, electrons have these states given by a certain energy-momentum relation. But one of the things we'll talk a little more about later in the course is that usually these states come in pairs. So anytime there is states available for, say, up spins, there is an equal corresponding amount for down spins. And so when we calculate density of states, whatever number we get, you need to multiply it by 2 because there's upspin and downspin. Now what is more is that in many solids there are all these valleys that are involved. That is, you have an overall energy momentum relationship may look something like, let me draw it here. So energy versus momentum in the overall solid may look something like this, with the electrochemical potential running somewhere here. And what you then do is, you say, well, basically we got these 3 valleys, and around each one, you have some kind of an energy-momentum relation. And of course, the 3 usually don't have to be identical, but in many cases, the different valleys have the same mass, because one of them may be in the x direction for momentum, another may be in the y direction, etc. And these are accounted for then with this overall g factor, the factor that we call the degeneracy factor g, which is equal to 2 for the number of spins, as I mentioned, times the number of valleys. And so the way you do it is calculate conductivity as if you got just one valley, as if nothing else to worry about, just one. Good. But then if you have, say, 6 valleys, that's fine. At the end of the day, multiply the answer by 6. In any case, you have to multiply it by 2 to account for the 2 spins, because whatever we discuss for electrons without talking about spins, there's one for up spins, one for down spins. And it gives, because the 2 are kind of what electrical engineers would say in parallel, that is, this conducts and this conducts. Together, they conduct twice as much current, which means twice as much conductance, half as much resistance. And so, you always have to multiply by the 2 anyway for the spin, and then depending on the solid involved, we have to include the valleys. So, when you're trying to model then the conductivity of any solid, first question we ask is, what is the energy momentum relation? Another question, if you want to really get quantitative and look at experiments, is the number of valleys. And that, in the context of graphene, that number would be 2, which means our degeneracy factor G would be 2 for spin and 2 for valleys would be 4. And that would have to be factored in as described in the notes. I won't go through it, but in the notes it's explained where the G goes in, that degeneracy factor, which is needed if you're trying to get numbers to compare with experiment. That's it.
Check it out now, y'all.
NanoHub U, online instruction.
Welcome to module 2.5 of week 2. And just to remind you what we are doing, again, in week 1, we obtained an expression for conductance, and in terms of the time it takes for an electron to get through a conductor. And from there, we obtained two important results, namely an expression for the conductivity. And this was obtained by considering a diffusive conductor for which the time that it takes for an electron to get through is proportional to L squared, proportional to the square of the length divided by the diffusion coefficient. So using this expression, we obtained an expression for the conductivity. And by considering a ballistic conductor where T is proportional to L, so it's just length divided by the average velocity, that is how we obtained an expression for the ballistic conductance. So these were the two important results from last week. And what we have done so far in this week is used a model that tells us how to calculate density of states. And the basic idea was that you think of these electrons as waves and that it fits into a box. And from that you can get the density of states. Okay. Now, everything we have talked about this week dealt with the first relationship, this conductivity in diffusive conductors. So what we're trying to give you was a feeling for how this conductivity expression can be used. Now, what I want to do in the last two modules of this week is we'll focus on this ballistic conductance, the second one, and use the same model, the model based on which we calculated density of states and all that. And what we'll show is a very important result that I'd say is kind of one of the seminal results of mesoscopic physics and in terms of small conductors, is that this ballistic conductance can actually be written as Q squared over H times M, where M is like an integer. And this is not obvious looking at this expression that we have obtained, because here we had Q squared times density of states times velocity, which doesn't have to be quantized or anything. It could have any value. And what I'll try to explain is why that quantity can actually be written as an integer divided by Planck's constant, M over H, where that comes from, that viewpoint. We'll explain. And this has actually been experimentally observed about 20 years ago. And I guess in the next module, I'll show you one of the typical experimental results. But what I want to do in this module then is just explain why this quantity here can be written in this form. Okay. Now, if we just accept what I've written here, then the expression you'll get for M, you could just view it as if we're just taking a bunch of variables and giving it a name. Right? What isn't clear is why that thing that we gave a name to would have to be an integer, but that will come to. But let's say we just gave it a name. What that means is we are saying that M divided by H is equal to dV over 2L times this 1, 2 over pi, or a half, depending on how many dimensions we are in. So all we have done is taken this expression from last week and said, let's write it in this form, where M is this new quantity that we are now introducing. So far, you see, this week we introduced two concepts. The N of E, which tells you the total number of states up to a given energy, and D of E, which is the density of states. And now we are introducing a third concept, modes, M of E. And while density of states actually is a rather old concept that dates back to the earliest days of solid-state physics, the concept of modes, this M of E, this you won't see much before, say, 1990 or so. This is something that became popular, got to be used a lot with the rise of mesoscopic physics. That is when people started making measurements on small conductors and ballistic conductors, essentially. Okay. So now the question is that this is this quantity that you have defined. What would it look like? Could we obtain an expression for this, making use of what we have done earlier this week, especially this relation that we said would apply in general to, I guess, any energy momentum relationship. That is, d times v times p is n times the number of dimensions. So what I could do is, here, instead of this d times v, let us write n times d over p. So it will be n times d divided by p. So all I did was, instead of dv, I'm writing n times d over p. And of course, this d is the number of dimensions, so I could as well include it inside here. That is, 1 remains 1. This 2 over pi actually becomes like 4 over pi. And d being 3, it becomes 3 halves. So you could write it something like this and take the d off from here. Okay. So now n, you see, is, we have an expression for it already here. Okay. Now, so what we are trying to do is find an expression for m, capital M, and that's equal to h times this quantity. So it looks like h over p times n over L times half 2 over pi or 3/4. I just took the 2 in there. Okay. Now n is this p over h to the power the number of dimensions. So when I multiply it with h over p, what we get is, so supposing I'm just using the n from here and replacing it with this expression here. So what we would get then is m is equal to, you see, h over p times this, which would be like, let me step back a little more, equal to p over h times d minus 1. Why? Because I had p over h to the power d, and then this is just the inverse, h over p. So when I multiply, I get p over h to the power d minus 1. And then there's this L here, which cancels out that L. So you would have 2 or pi w or 4 pi over 3a. But then I also have to account for these factors that I already had. So there's a half there. So the half and the 2 would give me a 1 here. Then there's the 2 over pi and pi w, which would give me 2w. And there's a 3 over 4 times 4 pi a over 3, which would give me like a pi a.